This huge reservoir, dam, and power plant are located amid the beauty of the Canadian woods at High Falls, which is about 20 miles from Copper Cliff, Ontario. Here, water is stored for use in the hydroelectric turbines that generate the needed electric power. This power is carried over high-tension transmission lines to the company's mines and plants in the Sudbury district. The Sudbury ore deposits were first discovered in the early 1880s. Today, these Canadian ores produce an abundant supply of copper, platinum, and other precious metals, and the world's largest supply of nickel. The famous Creighton mine has already produced millions of tons of ore and has unlimited latitude for further development. This new shaft was completed in record time by a picked crew of miners. It is 4,000 feet deep, and these pictures were actually photographed at the bottom of that shaft. Nickel irons and nickel steels made this giant hoist possible. With its modern methods and equipment, the Frood Mine is the world's greatest nickel mine. From the Canadian forests come the millions of logs which are in constant demand and needed for use as mine timbers. Other industries must supply thousands of feet of drill steel, which is reconditioned daily in the company's steel shop. Thousands of tons of railroad equipment and other materials of construction must also be purchased to properly operate this great mine. Let's join these miners going to work underground. Because of the importance of nickel, nickel alloys, and its associated metals, this mine is in constant operation 24 hours each day, and thousands of men are engaged in this work. To break out the thousands of tons of ore which are daily hoisted to the surface, miners with compressed air drills drive long holes into the ore body. These holes are loaded with dynamite and the ore is blasted out. The broken ore is shoveled by hand or mechanically mucked into chutes leading to the level below. As soon as this is finished, heavy timbers are brought up and immediately set in place to protect the men and prevent any danger of cave-in. Electric trams deliver timbers and other supplies throughout this miracle city underground. A careful engineering plan has been worked out so that the mined ore can be properly handled and not tie up the mine traffic system. This was accomplished through the use of storage chutes, from which the ore is loaded into cars and trammed to one of the underground tipples. There are two types of tipples in use in this mine. The rotary tipple automatically turns the car upside down to dump its contents. The Granby tipple unloads the car from the side. Both deliver the ore to a rock crusher located on a lower level. The ore, first crushed underground, is hoisted up the main shaft to the rock house. Here, the skip dumps the ore over a grizzly and onto a conveyor belt from which it is carried to another crusher. The shifts are divided into groups. Each has a definitely appointed time to arrive at the loading stations. To bring to the surface the thousands of miners who have just completed their shift and lower other thousands replacing them required a carefully worked out schedule. Miners arriving at the surface check in their time, use the facilities of the modern wash house and drive home in their cars. From the rock house at the mines, the ore is brought to the receiving bins of the concentrator plant, where it is further crushed and ground. From the crushing and screening plant, the ore is carried to this huge battery of rod mills, where the ore is further ground and pulverized in these barrel-like revolving drums. The pulverized ore is washed into the classifiers where a sizing separation is made. The undersize goes to the flotation department, the oversize is reground. Here in the flotation tanks, through a process which is well known, a rough though effective division of the nickel and copper sulfides is made. Air forced through the pulp creates these bubbles, which carry selected particles of ore with them. This is waste material which is called tailings. From the top of one of the smelter stacks, we see the country surrounding Copper Cliff, and in the background, the Stanley Stadium, one of the finest recreation buildings in Canada. Even in the hustle and bustle of mine, smelter, and refinery activities, this nickel community takes great pride in its appearance. This largest of all nickel smelters operates continuously, and the men work in shifts. An early morning shift, now off duty, is on its way to their modern wash house. The concentrates processed in the flotation tanks are thickened, filtered, and dried, and then are passed through a series of roasting furnaces to remove excess sulfur. The charge in the reverberatory furnace is calcined concentrates. This furnace separates the material into a metal matte and waste slag. The metal matte is drawn off into ladles and then is charged into the converters. The slag from the reverberatory furnaces is tapped into 20-ton pots, hauled out of the smelter and dumped. It is sometimes necessary to loosen the sculls with a dash of water. It's an inspiring sight when the sun's rays are piercing the smoky atmosphere to look down the long converter line and see men and machinery manipulating the white-hot matte. Molten matte is poured into the converter, air blown in, slagged off, and another step in the purification is accomplished. No outside fuel is applied to these converters, although intense heat is generated by this treatment. The molten matte from the converters is poured into a huge ladle and placed on the transfer line, which under electric control pulls the car into the Orford department. In this process, sodium sulfate is added and also some cold matte to control the temperature. Here it is picked up by a 50-ton crane and carried to a basic converter. The molten mix is allowed to stand while a primary separation takes place. The copper sodium sulfide is later taken to the acid converters, and the heavy nickel sodium sulfide goes to the cupola furnace. The parting of nickel from copper comes to a head in the Orford process. In the cupola furnaces, a chemical action makes the final separation between the metals. The nickel sulfide sinks to the bottom, and the copper sulfide remains on top, hence the term tops and bottoms. When the metal is tapped off into pots, cooled and dumped, there will be seen a very definite division between the two metals. The nickel bottoms are shipped to Port Colborne for further refining. The copper sulfide is blown to blister copper in these acid converters. The slag that is skimmed off goes back into process. The blister copper is tapped into ladles and then poured by crane into a specially designed hot metal car. This car delivers the metal to the company's copper refinery over a mile away. The hot metal car from Copper Cliff has arrived at the Ontario Refining Company plant with approximately 150,000 pounds of blister copper still molten. This heat is transferred to the loading furnace for further processing. One of the latest developments in copper refining has been the application of electric arc furnaces. The installation is extensive, requiring large transformers, control board, and other electrical and mechanical equipment. This most modern and up-to-date copper anode casting plant is capable of turning out 100 tons of cast copper anodes each hour. 2 casting wheels serve each anode furnace. Copper molds are used to promote quick chilling of the cast metal. The smooth flowing casting operation is mechanically controlled by the operators on this platform. Water sprays are used to chill the hot metal, after which the anode is removed from the mold and hung in a cooling tank. Later it is taken to the electrolytic refinery. The tank house of the electrolytic refinery covers nearly 4 acres. It takes about 14 days for a cathode to grow to market size so it can be cut to customer specifications. A large quantity of copper cathodes is resmelted in the refinery and cast into wire bar and other special forms. The smelting plant at Coniston, located about 10 miles from Copper Cliff, employs a different type of ore treatment. A series of blast furnaces are charged with selected ore and suitable flux to produce a special quality matte. A battery of basic converters treats this matte until it has reached a very high metallic content. One product of this smelter is a special matte which is returned to Copper Cliff for separation into copper and nickel. The Coniston final product is about 20% sulfur and 80% metal, carrying a ratio of 2 parts nickel and 1 part copper. This matte is poured out into slabs, broken up and shipped to the Huntington, West Virginia plant for the production of Monel. The Port Colborne refinery is located at the entrance of the famous Welland Canal. Here the nickel bottoms from the Copper Cliff Orford process receive their final treatment. The bottoms are first crushed in the ball mills. The material is then loaded into large tanks where it is leached, washed, and dried. This product is called washed nickel sulfide. Some of the sulfide is roasted twice in long calciner furnaces. The first roast drives off a large part of the sulfur, and the second roast leaves the material practically sulfur-free. It is called black nickel oxide. To make high-purity electrolytic nickel, the washed nickel sulfide is roasted on a sintering machine. This process sulfur and forms a clinker of crude nickel oxide which goes into the production of nickel anodes. The sinter or crude nickel is mixed with coal and melted in the oil-fired reverberatory furnaces and in turn is tapped into the anode casting wheel holding furnace. Each mold is carefully cleaned and prepared before receiving the metal. The holding furnace is tipped and the molten metal pours into the molds. The casting wheel is controlled by a trained operator. Each anode is equipped with a heavy bar to support it in the electrolytic tanks and to form an electrical contact. The finished anode is removed from the casting wheel. The electrolytic tank houses cover approximately 15 acres of space. Here, the crude nickel anodes are slowly dissolved and redeposited as pure nickel cathodes. After 14 days, they are removed from the tanks. Electrolytic nickel, with its extremely high purity, is used principally in making nickel alloys. The cathodes, which are normally 27 by 36 inches, are cut into squares of a size convenient for the alloy manufacturer. Nickel shot is made from electrolytic nickel, which is melted in the reverberatory furnaces. The molten metal is poured into a stream of water to make the shot, after which it is collected in a large tank, dried and packed for shipment. The company's works located at Huntington, West Virginia are the source in America for rolled nickel, Monel, Inconel, and other nickel alloys. This extensive plant is modern in every respect. The Monel mat, which comes from the Coniston smelter in railroad cars, is loaded onto a conveyor and carried into the calciner building. The mat goes through a jaw crusher, is picked up by a bucket elevator, and raised to the ball mills for grinding. Ground mat is drawn from the storage bins into buckets. The calciner charge is carefully calculated and is made up of many buckets full of ground mat, each of which must be weighed. A hopper at the back end of the calciner receives the charge. The mat is moved forward in these long calciner furnaces by a series of mechanical rabbles. The sulfur is removed progressively as these heavy rabbles stir and push the mat forward. The Monel oxide, now sulfur-free, is drawn into buckets. It's done in this long refinery building, which is equipped with several types of furnaces. These are the high-frequency induction furnace, the gas-fired open hearth furnace, and the electric arc type furnace. The whole roof of this furnace swings to one side so that the charge can be dumped in by an overhead crane. When the furnace is fully charged, the top swings back into place, the electrodes are lowered into position, the current turned on, and the melting begins. This non-ferrous electric furnace will melt 40,000 pounds of metal at one heat. This 20-ton open hearth melting furnace is fired with natural gas. A crane dumps the metallic charge into hoppers on top of the furnace. The furnace man spreads the charge on the melting hearth. After several hours, the charge becomes molten. The slag has been skimmed off and the metal is ready for tapping. A ladle is brought up by the crane and placed under the tapping spout. The tap hole is opened with an iron bar and the white-hot molten metal rushes into the ladle. When the ladle is full, the tap hole is plugged with a ball of moist clay. The ladle is skimmed and taken away to pour. crane is taking this ladle of molten metal to the big electric furnace for further refining. The big furnace takes the molten charge through its spout. In the back of the furnace there is a door through which the melting can be watched. This door is used for skimming off slag that forms during the melt. Special fluxes are added to aid in the refining process. The pouring of an electric furnace heat is a spectacular sight. A crane brings up a heavy ladle to receive the molten metal and holds that ladle under the pouring spout. A tilting mechanism tips the furnace so that the metal pours out of the spout into the ladle. As the furnace tilts further, the crane lowers the ladle until finally the furnace is empty. The metal is then carried to the ingot mold pit. Ingots weighing 3,300 pounds each are cast in iron molds. Electric hot tops make the ingot solidify uniformly. When the ladle has finished pouring ingots, there is always a skull of slag and metal left in the bottom. This is removed by dumping into a slag pot. The metal is later reclaimed from the slag. The ladle goes away to be made ready for another heat. Ingots larger than normal have both the top and bottom cut off by a cold saw, so that only sound metal will go to the forging hammer. To maintain the highest standard of quality in finished products, the rough outer surface of each ingot is cut away by powerful milling machines. Some of these machines mill 2 ingots at the same time. Ingot quality in this plant is a must. These mechanical chipping machines remove any imperfections which have not been eliminated in the milling operations. The heavy piece of metal is easily handled, and the machine operator can move the chipping blades to any part of the surface. Any minor ingot or sheet bloom surface defects have been chalk marked by a trained inspector to guide the machine operator. The ingots which have been thoroughly overhauled are placed in the forge shop heating furnace. The forge shop has a battery of powerful steam hammers. The white-hot ingots are taken from the furnace by this powerful machine and are delivered to one of the heavy forging hammers. The transfer to the hammer is completed by these huge manipulators which also hold the ingot while it is being forged. This equipment, which reminds one of a prehistoric monster, is controlled with such mechanical precision that it seems almost human. It takes the ingot from its mate, swings around, and comes forward to place it under the hammer. Once the ingot is placed on the hammer die, it is forged with tremendous blows. It would seem that this tough metal were more like a piece of butter, as the heavy hammer reworks the ingot structure into a denser, tougher structure characteristic of forged nickel alloys. The ingots are formed into square blooms to make rods and into flat rectangular blooms to make sheet bar. Sheet bar and rod blooms are standard products and account for the major part of the production. However, this massive equipment is capable of producing special heavy forgings weighing as much as 16,000 pounds. When the ingot has been hammered down to the proper size of bloom, it is cut to the desired length under the hammer. One ingot will usually make 3 rod blooms or 2 sheet bar blooms. The blooms are reheated in these gas-fired furnaces under non-oxidizing conditions. When ready for rolling, they are removed from the furnace and carried to the 24-inch mill. This charger, without any waste motion or loss of time, places the bloom on the mill runway. From this point on, the rolling is mechanically handled by an operator on the control bridge above the mill. This bloom is being rolled into sheet bar, and under the watchful direction of the bridge operator is passed back and forth through the rolls until the sheet bar has attained the proper thickness. The sheet bar now being at the required weight per foot, the rolling is completed. It is passed through the mill for the last time and automatically transferred from one side of the mill to the other. Still controlled from the bridge, the long sheet bar is carried down this runway to a hot shear at the end of the mill. Here, the sheet bar is cut to the specified lengths needed in further processing. Billets are also reheated in a gas-fired furnace in a controlled atmosphere. When removed from the furnace, they are taken by another type of charger to the 20-inch mill to be rolled into rods. The white-hot billet is passed through the rolls, then from the back of the mill it is transferred to another set of rolls. After it comes through to the front of the mill, it is carried back to the first roll unit and passed through again. Having gone through the roughing rolls of the mill, the bar is transferred to the finishing stand. Here, through the careful guidance of the roller, rods of a very exact size and shape are produced. Billets for the 9-inch wire rod mill must also be reheated to prepare them for rolling. During this continuous operation, the billet is handled with perfect rhythm. The attention and the efforts of each man must be timed to the split second so that he can properly carry out his part of this work. As this wire bar comes out, watch this expert catch it, clip the end, and again send it on its way through the mill. These operations must be fast and perfectly handled to be completed while the metal is still hot. A great deal of space is needed to carry on this work. As the wire rod continues on its way, it is always being reduced in diameter and lengthened with each operation. Here is another example of the careful timing necessary in this wire process. These two-man teams must handle their part so as to maintain speedy action. The original bar has now been rolled into wire and is ready for the final operation. The wire is automatically picked up on a rewind and coil. Sheet bars are reheated under an extremely close control both as to temperature and atmosphere. When ready for hot rolling, a pair of bars are withdrawn from the furnace and rushed to the mill. The first operation is known as breaking down. The sheet bars are passed back and forth through the hot rolls until they begin to lose their heat. Then they are returned to the furnace. Following the second reheating, the bars are brought back to the mill for further hot rolling. With each pass, pressure is added to the rolls to reduce the thickness and increase the length of the sheets. When the hot rolling has reached a certain point, the sheets are taken to what is known as the finish reheat furnace. In this furnace, the non-oxidizing atmosphere is controlled to hold the carbon monoxide content to a very close limit. When the sheets are removed from the finish reheat furnace, the final hot rolling is carried out. Heavy sheets are rolled one at a time, but as many as 8 light gauge sheets may be rolled together in a pack. 2 men handle the sheets or packs as they are being finished. When the hot rolling is completed, the sheets are taken from the mill and allowed to cool. The edges of the sheets are trimmed by shearing. Sheets are separated, carefully inspected, and gauged for thickness. Hot rolled sheets must go through a finishing process, the first step of which is annealing in a long, continuous furnace. Inside the furnace, combustion is carefully controlled. Having gone through the combustion chamber, which is followed by a cooling chamber, the sheets, now uniformly soft in temper, emerge at the discharge end of the furnace. The sheets are then pickled in acid and washed to clean and improve the surface. In the cold rolling department, these high-pressure mills with carefully polished rolls burnish the surface of the sheets and add special physical properties which are required for certain industrial uses. Cold rolled sheets are flattened by a roller leveler machine. Standard 2-high cold mills are used where heavy reductions are not necessary. Through the mill over the top roll. Care must be taken to protect the surface of the sheet and preserve a uniform and accurate gauge. The highly finished sheet is covered with paper to protect it. Cold-drawn products are processed in this department. The draw benches in this department are of various sizes. Some draw 2 bars or tubes at a time. This draw bench is both roughing and finishing. This heavy bench will draw seamless tubes of about 4 inches in diameter. Produces both the wall thickness and the diameter at the same time. Before tubes are annealed, it is necessary to wash off all traces of lubricant. The rods are very accurately straightened in a Medard machine. On this tube reducing machine, very heavy reductions are possible and exceptionally long tube lengths can be produced. The tube is reduced over a tapered mandrel by means of a specially designed die. Flat bars are sometimes cold drawn to meet unusual specifications. Some heavy wire is produced which is drawn from individual coils on this 4-reel bench. Strip is cold rolled in a department by itself. Mill train handles ordinary production. The end stand is called the finishing stand. The strip from the final pass is carefully checked for gauge. The heavy reductions and close tolerances required in nickel alloy strip rolling have made it necessary to install a high-pressure cold mill. In the Steckel mill, the strip is pulled through the rolls. The steps in process are carefully checked. Controlling devices enable this mill to meet very exacting strip specifications. Special finishes are produced in the polishing department. These machines grind with an abrasive belt. Their construction must be heavy and rigid. The sheets are clamped on the carriage and moved slowly back and forth under the grinding belt. Several grades of belts are needed to produce certain desired finishes. After the polishing operation is completed, a minute inspection assures a uniform finish free from any flaws or imperfections. It is easy to understand why this mirror-like metal surface is carefully protected with soft paper. Polished sheets are sheared to size and packed in crates for shipment. Metallurgical knowledge and skill, strict specifications, and carefully trained inspection makes for the highest standards of quality in these mill products.